All right, who would have known such drama, right? So it is with Leibniz's discovery that we are able to use the integration notation that we will discuss further down. After we go over this example, we'll talk about how Riemann sums relate to integration, and then we'll focus on integration for for today, and then also for the remainder of this chapter, we do integration techniques. Okay, so I believe we are on page 6, and the last time we talked yesterday, we were in the process of graphing this velocity table of values given time. We're going to go back and read the question, and it asks us to consider the speed of the runner, which increases steadily during the first 3 seconds of the race. Her speed at half-second intervals is given at the table in the table below. Find the lower and upper estimate for the distance that she traveled during the 3 seconds. So notice that it didn't say left or right Riemann sum. However, that's usually what they ask for on the AP free response questions. So just as a reminder to you guys, refresher of what we did yesterday, if I was looking at these intervals and asked to find, oh, and also it didn't tell us in here how many intervals to split it by. So we're gonna assume a half second for the distance that traveled during the first 3 seconds. Okay, so we're gonna assume that the subinterval is a half a second. So looking at your first subinterval, if they had asked me to find or approximate the area underneath this curve using a half second as a subinterval, then I would have determined that the left Riemann sum would be based on this coordinate point for the first subinterval. For the next subinterval, it would be based off of this point, and then the interval after that would be this endpoint. Now I'd like you guys to, with your pen or pencil, go ahead and draw. When we're asked to find the lower estimate, we're going to have to determine, is the left endpoint or the right point going to give me a rectangle that gives me an under or over estimate? So in this case, the lower estimate is going to be dependent on the left endpoint. So the first rectangle that I'm going to draw really has no height at all with a width of 0.5. Now let's go ahead and draw the next one. If it was a lower estimate on the next subinterval, my rectangle would be based off of the left endpoint. So this is just a visualization on the first 2 subintervals of what the lower estimate would look like. Okay, so basically you guys are summing up the area of all those rectangles. Can you guys type into the chat, what's the width of each one of those rectangles? What's the width of each one of those rectangles? Okay, so let's say they all have 0.5. So we're going to go ahead and factor the 0.5 out, leave the 0.5 on the outside. And now the height of each rectangle is determined by whatever y value on the left or the right endpoint that would give me a lower estimate. So for the first y value, we have 0. What would be the next y value that I would use from there going on? Okay, so 6.2, good. And so you guys can see that really the left endpoint is going to give me the lower estimate. That makes sense because my function is increasing. So I would go all the way up to 19.4 and stop there. Can I have you guys go ahead and try now the upper estimate? And I'm going to erase my rectangle so you guys can see the first subinterval. So if I erase my first rectangle, oh darn, that erased too much. Okay, so my first rectangle on the interval from 0 to a half, if I wanted to pick an over estimate, would be dependent on the right endpoint, and that's going to go over the curve. So go ahead and type or write out what your upper estimate is going to be. You guys don't have to type it out, just go ahead and write out what you think it is. And then go ahead and double check your answer. Are you guys doing okay so far still? because we're gonna just talk about how Riemann sums lead us to integration, but any questions so far? Are we doing okay on the lower upper estimate? Can you guys type yes or no into the chat? I can't see your faces. Okay, thank you guys. Are there any questions about are there any questions about what we just did? And we'll do another example on this just to reinforce the idea of using rectangles and table of values as well. So I am going to have you guys. Sorry for the cutoff, but I don't know why this happened right here on the far right. You guys see a note, and then there's a description of the above. So I'm just going to have you guys read that for a moment and then explain the link between Riemann sums and integration. Okay, you guys, yes or no in the chat. Have you guys seen this summa notation before in your previous class? Like that symbol right there. Have you guys seen that before? I believe you would have seen it in when you studied series. Okay, so that summa notation is going to be the focus of when we get to series at that infamous last chapter that we that a lot of the former students had talked about being the hardest chapter. This notation is just a shortcut way of saying the sum of, and the way that we read that is the bottom value is where you start off. So if I starts off with 1, I would plug 1 in and say that, okay, I'm going to increment this starting at x of 0. Or if they wanted you guys to, and they would define it like let I start at 1 or let it start at 2, and then n being some number where if we wanted to fix it at 4, that would be the last value that we would see on our general term over on the far right. So you guys can see this is just the general notation for what we've been doing. Notice that change of x represents the width of each one of the rectangles, and change of x happens to be in all of the terms that you guys see on the right. So if I were to factor out the change of x, what we were doing when we were writing our sums was just writing the corresponding y values. So that's the first y value, second y value, that's what the little subscript means, all the way up to the nth y value. And so the idea is that for our purposes, when we're coming up with an estimate, we'll all have a finite number of rectangles. But a Riemann sum is taking the idea, and I think someone threw it out there yesterday, of letting n go to infinity. So instead of just looking at 6 rectangles or 10 rectangles, what happens if we let n go to infinity? And so you stick this limit in front of the series notation down there. And what this is saying is you let n go to infinity, and what happens is the more rectangles you guys have, what happens if you guys add more rectangles? What happens to the width of each one of the rectangles? What happens to change of x? What happens to the width of the rectangle? It gets smaller, it decreases. So the idea that was in the video about getting it, discussing really, really small values, and the idea of a limit allowing us to study what happens if we take an infinite number of rectangles, add them together, and as we do that, as we increase the number of rectangles we have, the change of x, or the width, gets smaller and smaller. Okay, so this notation is the notation that they discussed where Leibniz, we eventually adapted Leibniz's way of describing the area underneath the curve using, instead of the summa notation, it was replaced with that integral notation that you guys see on the left. So this looks like a letter S. That's the integration notation. Okay, so just to give you guys some vocab words right here. The A and B value are what we call are limits of integration. Okay, so if you look at A and B and think about what we had above in our graph, A and B represented your left endpoint of your area. So let me point that out here. Okay, the far left, if my interval starts at A and ends at B, that A and B value is now on the limits of integration, A and B. So it tells you where to start and where to end. Okay, the f of x part is what we call the integrand. So inside here, this expression right here is called the integrand. And another way of describing change of x is a differential, and the notation for dx means the same thing. We let x get really, really small, or the change of x get really small. So change of x is dx. So we transition from this limit summa notation that's complicated to one of an integral. Okay, so the limit is called the Riemann sum. For our purposes, when we're looking at reasonable estimations of integral problems, we're going to think of a finite number of rectangles. So 6 rectangles or 10 rectangles, whatever is reasonable. So flashback to, I don't want to say it was a nightmare, but this is the year I took my AP test. I know students ask me, do you actually remember those questions, Mrs. Kim? No, I don't remember the questions that I took when I was taking AP Calc. But in this particular problem, go ahead and read. I'm going to do one example on this with you guys and then transition into something else. So go ahead and read this example. Okay, so I am going to leave you guys to do A, B, and C eventually, because those are questions we've done before. I can go over them if you guys have questions eventually, but we're going to look at D, which is the new part. Okay, so here we have that they want us to approximate. So notice that now they introduce this idea of an integral. Okay, so when I read this integral, this is saying find the area underneath the curve of V of t on the interval from 0 to 50. If I look at my graph, they not only provided me a table of values, but they also gave me the graph of the velocity function. And all of these points are plotted over here on the left. Okay, and so they did say that the intervals you would notice are jumping by 5s. And on here, they want me to approximate this using Riemann sum. So I know area of rectangles. And then also by midpoints of the 5 intervals of equal lengths. Use correct units, explain the meaning of the interval. Okay, so let's first start off with, if I had 5 intervals and only 5 rectangles, what would my change of x be, or what would the width of my rectangles be? Okay, sometimes you guys like this one. It's really easy for me to see visually what that it would be 10. But if you guys want a way of calculating it by doing b minus a over n, this is, I'm also showing that in the notes here. So 50 minus 0, the whole entire interval divided by the number of rectangles I want is going to give me the width. So again, this is the width of the rectangle. And so what we're going to do is take 10, put it on the outside because all of the rectangles have 10. And so here is where it varies, the y values. Which y value is going to give me the height? So it's either the left endpoint, the right endpoint, or the middle. So I'm going to go to my first subinterval, and I'm going to look at my first interval from 0 to 10. Okay, this one is directing me, hey, use the y value from the midpoint. So the y value from the midpoint is something on the graph, right? So one mistake students might do is like, oh, reading the graph, that looks like the midpoint would be a y value of 10. Make sure that you guys go back and double check that the midpoint is really that, and it's not, right? It's actually 12. So you're going to do exactly f of 5 plus f of 15. And so you guys can see the midpoint of your subintervals occur 10 units apart, 25, 35, 45. And so I'll kind of just point out mistakes that I see, you guys. So at this point, I recommend, if you guys want to like just be really thorough, that you write out what I see someone type out in the chat. Okay, so f of, I want the y values, not the x values, but the y values at the midpoint of each one of the subintervals. And I should end up with a total of 5, which I do, y values. And then from there, go ahead and take that step of now, well, what is f of 5? Go back to my table of values, and f of 5 is 12. So then it's 12 plus 30. Sorry, I'm going back and forth here. Actually, it might help if I do that. 30, 70, 81 plus 60. Okay, so then at that point, if you guys were doing a free response question and there's no like trick to it and it's just a matter of simplifying, you technically can leave that. You don't need to. This was on a non-calculator section, in which case you guys can just leave your answer. Or if you guys come up with the simplification of what that is, it would be 2,530. And then don't forget the units of measures. That's going to be important. So we've accumulated. So again, remember when you guys are finding the area underneath, actually, I see one person type it out, but I don't think it's correct. Okay, if you guys are integrating velocity and you're finding the area underneath the curve, what does the area represent? It represents an accumulation of something, right? So no, the derivative of velocity is acceleration. Maybe go back to this example I had discussed before. If my velocity was just a horizontal line, yes. If my velocity is 60 miles per hour and I go for 2 hours, then the area underneath the curve, 60 times 2, represents the total number of miles that I've traveled. So in this case, the units of measure when I integrate velocity happens to be feet. And when they say explain the meaning of the integral, then it would be that, what was this, a car? The car traveled a total distance of 2,530 feet. Okay, so when you integrate velocity, whatever rate of change that you guys are integrating. So if it says feet per second, your accumulation is the feet. Your accumulation is the distance in this case. If the rate of change happens to be the amount of liters leaking out per second, then your accumulation would be the amount of water leaking out per second would be the amount of water that leaked over that time period. Okay, so it's an accumulation of the unit of measure. That if you guys had like a rate of change, it would be, for example, velocity, the rate of change is miles per hour, it would be the accumulation of the miles, in this case, feet. All right, I also took that same table of values, and let's say that they did give you guys a table of values, which I noticed that the more current free responses, they actually don't give you guys the graph. And I think the graph is helpful for us to visualize the rectangles. So what I did was I took the graph, and what I usually do, if you guys look at the camera, is I flip if I only are given a table of values, I might flip my paper like this, the way that you guys see it on the screen. And so if they want me to divide the graph into subintervals of 10, I might just actually do that on here and just go, okay, well, this is 10, 20, 30, this is my rectangle width, 40, and then 50. So this gives me my change of x. So that's the width of the rectangle. And then if I'm doing left Riemann sum, then I'm picking the left y value of each one of these subintervals. Okay, so that's kind of like one technique that I would suggest doing if you're just given a table of values. Now, if I wanted the right endpoint, what would change is now looking at the subinterval from 0 to 10, I'd pick the 20, I'd pick the 55, the 78, 75, and 72. And then lastly, what we just did was the midpoint. So then I would pick the 12, the 30, and notice that these are the y values that are plotted. Does that make sense as a visualization to you guys for the table of values? Okay, kind of like split it. Instead of having to plot the entire thing, you guys can just like pick the y values that you need to determine the height. So that's a quick and easy way to interpret the table values. The other new development since 1998 is that a lot of the table values provided to us nowadays are actually not equal subintervals. So they'll give you guys a table of values and it might be like 0, 5, 7, 9 as the x values here. And that's okay. So if I just refer back to my knowledge that Riemann sums is just the area of rectangles, my subintervals now just have to calculate individually. It might not be a fixed value, in which case I just basically come up with and crank out each one of the rectangle areas and then add them together. They usually don't give you guys a ton of those, but I mean, a ton of rectangles to do, but it's something to keep in mind. And we will definitely see examples like that as we move further into this chapter. Okay, so on a sheet of paper, let me see the time here. Okay, on a sheet of paper, I think I'll start this off with you guys and see how far we get here. Okay, so I'm going to introduce the idea of an integral to you guys and what it means to find something called the antiderivative. Okay, so this is going to be integration as anti-differentiation. What do you guys think anti-differentiation means? What do you guys think anti-differentiation means? Oh, what does the word, yeah, opposite of differentiation. Exactly. I was looking for the word opposite or reverse or opposite. So you guys are going to reverse the process of taking a derivative. Okay, so this is just practice at this point of, and I spelled opposite wrong right there. It's just practice finding antiderivatives. It's going to be the early part of this week and then leading into the lesson that you guys have on after the test. Okay, so here is an example of what I mean. So let's say you guys have the integral, and we're going to talk more about the of the area and how it relates to the integral in the second part of the lesson. But as for now, when you guys see the integral notation, you're going to think of what the derivative of what function. So they're inverse operations of each other. Now we're going to think of the derivative of what function gives you guys x squared. Okay, so normally think of what you guys do with the derivative. With the derivative, you would bring the 2 down, and then you would have x, and then you would subtract 1 from 2. So the opposite of this would you would add 1 to the exponent 2 and get x cubed, and then multiply by, because there's a constant of 1 out front here, we kind of have to undo. So let's say you say, okay, well, the antiderivative must be x cubed. And you check your work and you take the derivative, well, the derivative of x cubed is 3x squared. Okay, and that's not what I see inside the integral as the integrand. So we somehow have to get rid of this 3. And to get rid of that 3, we would multiply by 1/3. So now let me erase all of this. Let me ask you guys, if you take the derivative of 1/3 x cubed, do you guys get x squared? Does that work? Okay, so if you were to take the derivative, you'd bring the 3 down and you would get x squared. So the shortcut way that you guys might see as a rule is that you would, for the power rule, it's the reverse of the power rule, you would do n plus 1 and then times by the reciprocal of that exponent. Okay, so kind of reverse the process of the power rule. Okay, so here is another question. What happens if I add 2 to that? When you take the derivative of 1/3 x cubed plus 2, do you guys still get back to x squared? Okay, so yes, you do, right? You plus 2 still works. So that means, like, roughly speaking, the graph of an x cubed function, let's say you guys had a third, you graphed out 1/3 x cubed without that plus 2, and you guys get some graph that looks like this, roughly speaking. Its derivative is x squared. Okay, and then what I did was I just said, okay, what happens if I added the 2 to it? So that would be a shift up on 2, and we still have the same function. And let's think about what the derivative function is. The derivative is the slope of a function. And if I were to draw tangent lines to any one of these curves that I'm drawing here, given that I drew it a little bit nicer, these are the exact same functions except shifted up and down by a constant value. And so we see that the slope, in theory, if I drew it nicely, at this point, at let's say -1 would be the same here, here, and here. How many of these curves can I draw that would have the same derivative? Infinitely many. Okay, so, and they all differ by what we call a constant of variation. Okay, a constant of, a constant of integration. So that +2, I'm going to replace with plus c. Okay, so this is what we call an indefinite integral. Okay, so over here, let's call this an indefinite integral. And an indefinite integral is we're coming up with a family of functions whose derivative happens to be the integrand or what you guys see inside the integral. An indefinite integral always has a plus c. So I can't remember if that one video that you guys watched with the girl singing, if she was lamenting having to, or missing a problem because she forgot the plus c. An indefinite integral does not have the a and b part to it. So go ahead and just draw that. An indefinite integral does not have a and b in it. So it just means what's the family of functions that would give me the derivative that I see in as the integrand inside the integral. Okay, so 1/3. So let's go ahead and practice a few of these. I have some for us to do. So let's say example number 1, and we don't have to draw the graphs. We just have to practice doing the antiderivative here. Okay, so just like derivatives, if your integrand is inside like this, we can also take it, integrate term by term. Okay, so let's start with x squared. Okay, can you guys type into the, actually we just did x squared, so we'll say 1/3 x cubed is the antiderivative. Okay, what do you guys think the antiderivative is of 1/3 x cubed? Okay, remember, reverse what you guys did with the derivative, and this part is hard when we first started. Very nice, Brandon. Nice job. Very nice. And sometimes it takes us a while to get accustomed to it. So you might not get the answer like right on the second step. Let's say you know that you're supposed to increase the 3 by 1 to get x to the 4th, and then times by 1/4. Well, that's going to lead us to 1/3 x cubed plus 1/12 x to the 4th. Nice job. And please, when you guys are practicing your antiderivatives in the next few homework assignments, can you just verify and double check that when you do an indefinite integral, 2 things, that you add the plus c, and then also if I were to take the derivative of this, do I get back to my original, which I do. So just like doing a quick check to make sure that that makes sense. Okay, so that's how you guys would do it with the power rule. Okay, so this is a common basic integration question on the AP test. Okay, so very simple one that might not be so simple when we start doing all the complicated antiderivatives. For some reason, kids will forget this one. Like, how do I do this one again? It's not those advanced integration techniques. It's actually a basic one. Okay, so can you guys tell me algebraically, how can you guys simplify this so that you're just using power rule instead of thinking of this as quotient or product or reversing any one of those? Okay, yeah, you can bring up the x to the -1 and then distribute that or divide out each one of these terms by x. And I'm going to get to that question again. Someone asked me a question, so I'll answer that in a minute. Let me just divide that out. So x squared plus 2x. And then if I have a -1 that I'm bringing up, then that's plus x to the -3. So let me pause here for a minute. Someone just asked me, why did I add the plus c? The plus c represents a constant, like any constant. So if I had a plus 2 there, and I were to take the derivative term by term, that the derivative of 2 is 0, which you see is not in the integrand at all. So that's just to represent all of the entire family of functions that have the same derivative as this one. Okay, so the plus c, it could be plus 2, plus 3, plus 4. The derivative of any constant is 0. And so that's going to lead me to, there's a whole class of functions that then has the same derivative, and that derivative is inside here as the integrand. Does that make sense for the person who asked? So plus c always at the end, because the derivative of a constant is just 0. Okay, so some of us are starting to type in the answer. And it does take a bit of time to adjust ourselves to this new technique, especially because you guys are reversing the process. Just when you guys started to learn taking the derivative, now you're doing the reverse and finding the antiderivative. So very nice. The people who've typed in your answers are correct so far. So again, just term by term, we have x squared, increase this by 1, 3, multiply by the reciprocal, 1/3. X to the first, if I add 1 to that, 2, and then I multiply by 1/2, but 1/2 times 2 is just 1. And then lastly, this one, if I add 1, I get -2 times by the reciprocal, which is -1/2. And then don't forget, it's an indefinite integral. There's no a and b to it, so we add the plus c at the end. Okay, so let's see. What do you guys suggest if you see, here's another common basic integration one that you have to do something first to it. What do you guys suggest we do to this first before we integrate? Good, yes. All right, you guys go ahead and do that. Go ahead and FOIL it out for me. And then attempt this problem, type it into the chat and see what you guys get for it. Good job, those of you guys typing it in. Those look right. Oh, except for, I think one person forgot. Okay, so 2/3 x cubed minus 7 has x squared. And then how do we integrate plus 6? Technically, 6 is a constant, and it has an x with an exponent of 0. So if I increment 1 to x to the 0, I get x to the first, and divide by that to get 6x. Yeah, so plus 6x, good. And then plus a c at the end. Of course, you guys are going to get now questions like, what's the integral of secant squared of x? So just reverse, do the reverse and ask yourself, the derivative of what gets you guys secant squared? The derivative of what function got me secant squared? Yeah. So yeah, just reverse your thinking now, you guys. So tangent of x plus c, and the list of all the antiderivatives are on that cheat sheet that I gave you guys. One that is something to watch is if you guys were to integrate 1 over x dx. And I'm going to make this the last one. Because of the way that the function, the domain of 1 over x looks, its antiderivative, if you guys think back, the derivative of what function got you guys 1 over x? Do you guys remember? Yeah, so that's the tricky part. A lot of people want to say 0 for this because they do x to the -1 plus, it's not 0. And think of the fact that 1 over x actually looks like the reciprocal function. So its antiderivative can't be just 0, right? Yes, very nice, ln. But because of domain restrictions, whatever you guys have, the antiderivative of 1 over x, it's going to be the ln of absolute value of x. That's going to become more clear when we go into differential equations, why that absolute value is there. And when we solve for exponential growth and decay problems, things like that. But the antiderivative of 1 over x is ln of absolute value of x plus c. I'm not going to go over all the antiderivative rules, but you're just going to think of it